Right. Hello, everyone.
Hope you're enjoying the workshop. So it's time to get into some explosive phenomena on the sun. We have been talking about some high energy stuffs as well as some low energy stuffs. So this is something which really falls at the heart of studying solar physics. Why do we need to study the sun? That's how we have designed the workshop, and this talk is dedicated to understanding one of the most spectacular phenomena that happens on the solar corona, which are called as the CMEs. Yeah.
Oh.
Yeah. All right. So we go back to a small anecdote, which was on March 12, 1989, in the country of Florida. So if you have seen the map of Florida, Florida is not really a polar country, right? So it's not that high up in the poles. But still, there were some lucky people who got to see northern lights or the beautiful aurora borealis in Florida. So people were really excited and they took their photographs, but they were not sure that what is happening. And just one day after that, on March 30, 1989, and this happened in Quebec in Canada, suddenly people found out that although people were enjoying the northern lights still, one day after, in Florida, people in Canada were having a 12-hour power blackout. So it happened for 12 hours and it extended beyond 14 or 16 hours on the same day. And it took quite a bit of time for the community or the astronomers to go back and study some other data sources. And they found out that there was a sudden storm on the sun. And people were not sure what that storm means or what sort of storm is that. And people called it that, let's say it's a magnetic storm. And so the scientific community had a meeting and they decided that, okay, we need to understand these solar eruptions or how these storms happen. And after understanding, the story should not end there. We need to monitor these eruptions. And the best part is, or the most important part is to predict these eruptions. That when are these eruptions going to happen? If they do happen, what will be the directions of happening? And at what time are they going to affect the interplanetary space? And with that in mind, it was realized that although the Earth is the only livable planet in the solar system, but there is a much profound connection than they are just being two celestial strangers. So the sun and Earth are actually connected. And this term was coined in the community that we have a sun-Earth connection. And of this sun-Earth connection, this particular term called as the coronal mass ejection, so the CMEs, lies right at the heart of this connection. All right? So with that in mind, what I have decided is to, distribute this talk in a few questions. The first, of course, will be to see or to, let's say, understand what are the CMEs, how do we define the CMEs. Then we would ask that why do we need to bother about the CMEs, and then how to study, or if we do get to identify a CME, how do we work on them, or how do we analyze a CME. And then we will talk about some of the properties, some of the interesting properties, and you'll see that there are some really, really weird properties the CMEs often show us. And we are still not sure to come up with a unified explanation of all these properties taken together. Then I'll also talk about some case studies where people have talked about some peculiarities, which, like, there are good people, there are bad people. Some people like to play by the rules, some people just don't care. So the case studies are mostly dedicated to the ones which don't care for the rules. And I think those are the interesting ones because you don't know which ones is coming for you. And we'll finally finish up with some of the future possibilities, that where do we stand right now? And how do we look forward to, how do we plan our activities in the next 10 years or 20 years? So coronal mass ejections, as you can see here, are these beautiful explosions. Yeah. So you can see that the explosions are happening all across the solar corona. And people have tried to define it in different ways. All right. So what they have said is, these are magnetic explosions, which are made of plasma and magnetic field. So a part of the solar corona is blown up. Now, how does that happen? We'll come to it slowly. But then you will also see that the shapes and sizes of these explosions are largely different. It's not of the same sizes, right? So if you want to define that CMEs are magnetic explosions on the sun, then you would ask me that what happens here, these narrow stalks, which he was talking about as streamer belts. So the streamers are also leaking plasma. So the question you would ask is, should I call it as a CME? Now, based on what I have told you right now, it can be a CME. I am saying the CME is all, it's about just plasma and magnetic field. So when you have these sort of confusions with redundant definitions, what you do is you go back to your textbooks, right? So you just open up your textbook, and thanks to Tim Hundhausen and others in 1984, they coined a very complete definition of CMEs. They said that CMEs can be defined as discrete, bright, white light features. Now pay attention to all these three words, all right? First, what they say is discrete. So it doesn't have to be continuous. So it's like a discrete blob of mass flowing outside. Bright. What does that tell us? Why is that word important? So every time you read a definition in physics, we have realized that when we were kids, we were asked to learn the Newton's laws of motion by heart without missing a single word of the law. So why is that? Because every word has significance. And the same happens for this particular definition as well. So the word bright comes because there are also some dark features here. And those are the ones that will confuse you, that whether this is a CME or not. So the bright is the ones because they're intense, they're producing more emission, because it is more dense. All right? So it has to be something which is dense, which will be bright. It has to be discrete. And it has to be seen in white light observations. Okay? So that's how the definition came, because initially CMEs were seen for the first time in white light images. So how white light images? So you have been listening about the solar atmosphere since the earlier talk. Now, you know the photosphere, right? The visible surface of the sun. So what is the average temperature of the photosphere? Yeah. So the peak happens somewhere in the visible spectrum, right? If you apply Wien's law. Now, this photospheric light, when it comes out, it scatters off the coronal electrons. So there are coronal plasma, right? The corona is not vacuum. It's filled up with plasma, free electrons. So these electrons scatter off the photospheric photons. And these photons get reflected or scattered. And we watch the CMEs based on this phenomenon known as Thomson scattering. Are you guys aware of Thomson scattering? Wonderful. Okay. So we have these discrete bright white light features propagating outwards. Why is that propagating outwards word important? Because like every object, every object will have a gravitational field, right? So if you have a plasma moving out, you can also have a similar tendency of the plasma falling down due to gravitation, right? So we will consider only those as CMEs which will have an outward motion in the coronagraph field of view. Now they say that it can happen for a time scale of few minutes to several hours. What does that tell you?
They aren't perpetual.
Sorry?
They won't stay for a longer time, like the streamers.
No, it says that it can happen for a few minutes to several hours. So the time scale has a range. So what do you infer from that?
It can be faster, it can be slower.
Correct. Yes. So it tells you that the speeds of the CMEs can be largely different from each other. Some CMEs can happen with the speeds of a few hundreds of kilometers per second, let's say 200 kilometers per second or 500 kilometers per second, and a few can be of 3,000 or 4,000 kilometers per second. Recently, the coronagraph on board Solar Orbiter has discovered one of the fastest CMEs, and it's like around 5,000 kilometers per second. So based on the speed of the CME, you will see the CME moving outwards in a very short interval of time. So that's how they segregate and they try to unify all these sort of different CMEs into one complete picture. And with that picture in mind, this is the most common picture that if you Google coronal mass ejections in Google, this is the image that you will get in the first place. Now, why this picture is important? Because this picture tells us a lot about the magnetic morphology of the CME. So it is expected that a CME is made of something called as a magnetic flux rope. So let's say this is your sun. Now, a magnetic flux rope looks something like this, right? So this is a helical structure. Okay. Now, what do you see in this image? You see a three-part variation of the intensity. You have a bright part, you have a dark part, then a bright part again. Now, just a while back, I said that the brightness comes because of Thomson scattering, right? So Thomson scattering, what are the things that Thomson scattering emission depends on? Can anyone say? Electrons what? I mean, what are the parameters on which Thomson scattering depends? Sorry? No, what does the intensity depend on? I'm saying the intensity due to Thomson scattering. What does that depend on? I think I'm not getting you.
I'm saying the material density.
Oh, density. Sorry. Right, correct. Density and anything else? Anything else? No, that's the safest part that it does not. So yeah. So the other crucial part about the Thomson scattering is that it has polarization information. Okay. So the photon that gets scattered due to Thomson scattering, the photon gets polarized. And that polarized information is a secret information that we physicists extract out of it and get 3D information out of the scattered photons about the structure that is reflecting those. All right. So you can see that you have a bright front. So how does that bright front happen? So you can say that this region is density enhanced, right? Because it is bright. So how does the density enhancement happen? So let's say that this floor is filled with sand, all right? And if you try to have a broomstick and broom it, what will happen? The sands will accumulate in front of the broomstick, right? So the same thing happens in the sun's corona. It is filled with plasma, right? It's not empty. And suddenly there is an explosion. So it pushes against the plasma. So the speed of this structure is higher than the ambient speed of the flowing out plasma. So what happens is the plasma gets accumulated in front, right? And this density keeps on increasing for a certain range of heights. And you have this dense leading edge, which is the leading front of the CME. Why it is called the leading front? Because it is ahead of the rest of the structure, right? Now, since you were discussing about plasma beta, so this is a flux rope, okay? Now, if you remember, that active regions are magnetically dominated, and CMEs are also a magnetically dominated structure. So the magnetic pressure inside the CME flux rope is very high. So when I say it's very high, you should ask me that high with respect to what? So it's higher with respect to the thermal pressure, right? Because plasma is also there. But you have to keep the pressure balance, right? Every object, the pressure has to balance. So to keep the pressure balance, the magnetic pressure is higher, so the plasma is relatively much lesser inside the flux loop, and that's how you see this dark region inside it. Yeah? So this is where the flux loop is embedded. It's called as the cavity. Okay? So the dark cavity is somewhere, we say that the flux loop is there, and below this cavity, you see this loop, which makes the morphology of the flux loop. This loops, as you can understand, so the sun will have a gravity, right? So what will happen? The plasma that is accumulating here will try to fall back, right? So what happens here? It's a valley, right? So what happens at the valley? It's a local minimum, right? So plasma will start accumulating, right? So it's relatively denser here, it's relatively denser here. So these two regions are seen as two relatively denser regions. If you try to plot the intensity across a CME, you'll get two spikes.
So one more time I couldn't
Yeah.
4 pi.
Okay. So let's forget this. So this is your flux loop, right? So when you have plasma is everywhere, right? So this plasma will be trapped, part of the plasma will be trapped inside the flux, right? So this will also start falling down due to gravity. And this plasma will get trapped here, like small clumps, like a mug, right? So when the CME erupts, it will pull the lagging plasma with it. So this lagging plasma, which is dipping, or which is hanging on these dips, these are seen as the core of the CME. Getting some sense? Right. Yeah. No, bow shock is not associated with CMEs. Bow shock is associated with the planetary magnetic field. Okay? So when you have a planet, the planet has a magnetic field, and ahead of the planetary magnetic field, like ahead of the magnetosphere for the planet, you'll have a bow shock. Okay. Sometimes there is also a shock, which people often call as a bow shock for the CME, but strictly speaking, bow shock is mostly used with planetary magnetospheres.
Does this have a size and speed relation?
Size and speed of what?
Steam.
We have it. Just hold on for a minute. We'll come to it. Yeah. The cavity. Okay. So this is the region which is falling as the cavity. Because this region is plasma depleted. So it is hanging like this, right, in the solar atmosphere. So the plasma is trying to fall down. And in these dips, the plasma is getting trapped. It is hanging from the dips. And ahead of it, the plasma is getting accumulated. So inside the flux tube, just because magnetic pressure is higher, so it's relatively plasma depleted region. The density of plasma is much lesser. So since the density is lesser, the amount of emission that is coming due to photospheric electron scattering will be also lesser, right? So the intensity is less, and that's how we call it as a dark cavity. But interestingly, if you try to see the same CME in an extreme ultraviolet wavelength, it might look different. So this dark region, which looks dark in white light observations, might not overlap with the dark region in the extreme ultraviolet observations. Any idea why? Think about it. Just think about how extreme ultraviolet observations. I think, did you talk about this AIA wavelengths? Oh, you did. Okay. Yeah. So now, once you see the CME in a coronagraph disk, some basic parameters that are usually used, I should point out in the early phase. So this is the solar north, all right? So this is the coronagraph disk. We'll come to the definition of the coronagraph. So this is the coronagraph disk, and this is the CME as you can see here. So what is this part? This is the leading edge, right? So if you want to position, let's say if I want to ask you that where is the CME, how do you locate a CME on the disk? So the primary parameter that helps you to locate a CME is called as the position angle. Okay, so how do you measure the position angle? Let's say you want to measure the position angle of this part, this feature of the CME. You draw a tangent, simple, and you measure the angular angle of the tangent anti-clockwise from the solar north. So this will be somewhere like 180 degrees, right? So this will be another position angle. Now, if you take the position angles of the two extreme ends of the CME, the two extreme flanks of the CMEs, and you take the difference of that, you get the angular width of the CME. Very simple, right? All right. Now, the question is, why do we want to communicate? Now, these CMEs, as they travel outwards, they don't just remain confined on the solar corona. Okay? So after they get ejected, they travel outwards and they keep traveling outwards. They leave the solar corona and they enter into the heliosphere. And then they keep traveling into the interplanetary space. Now, as they do that, it is only a matter of very small probability, yet a finite probability, that some of the CMEs might be directed towards us. Okay. Now, if that is the case, then a CME which has a magnetic field like this, you see that these are the magnetic field lines of the CME, they come near the Earth's surface, and the Earth has its own magnetic field. And you have something called as magnetic reconnection. So in your BSc physics, you were taught that two magnetic field lines cannot intersect, right? Because it would mean that the Lorentz force is the magnetic field is acting at two different directions at the same point. But turns out that in astrophysical plasma, with the drastic conditions, your life is way more interesting than that, because the magnetic field lines can in fact reconnect. And when it does happen, there is an explosion. So this explosion is what are called as a geomagnetic storm. So I wouldn't go into the details of the geomagnetic storm, but this can lead to a lot of disruptions in the Earth's technological systems. There can be power grid failures, there can be problems with the satellite communications, all sorts of radio communications gets interrupted, something that happened in Quebec, Canada that I was talking about. Now, the interesting part, apart from the CMEs being a hazard, from a technological perspective, is that as the CMEs keep traveling outwards, they undergo through a lot of change. What sort of change? A change through their properties, the physical properties that they have. So when the CME takes birth, it has a certain range of properties, but as they go outwards, they keep interacting. Interacting with what? Correct. Not just the solar wind, it has its own properties inside. So those properties exhibit certain sort of characteristics which also change with height and time. And through this, the important part is it is important to capture all these changes throughout the different heights so that we can get to understand that once the CME arrives at the Earth or any other planet for that matter, how will that CME behave? All right? So the thing that we were saying is we come to the second part. how do we observe CMEs? Now, initially, what people used to do is, to observe the corona, people had to wait for eclipses, right? So every time there is a solar eclipse, although most parts of India do fasting, but the solar astronomers go outside and watch the corona. So then Lloyd came out and he said that, okay, we are greedy people, so we cannot wait for eclipses every time. So let's make our own eclipses. So this is something that's the basic principle of a coronagraph. So you take the starlight and you block the disk. For example, when you look at this light, let's say you open your torch of your mobile phones, you put it against this. You wouldn't be able to figure out the torch very well, right? Because the torch will be fainter than this. Once you try to block this light, the torch light will be more prominent. So the same thing happened for the solar corona. The photosphere is so bright that the faint corona is almost impossible to observe in normal days. So the only way to observe the corona routinely is to block out the disk. Okay? So that's what happens here. You have the coronagraph mask. So you have a mask in the center. You block the central rays, which comes from the disk of the sun. So you have something like this. So these are a collimated beam. All right. You put a stop at the center. So all the rays that are coming here will be stopped. So now the beam is like this. Right? Now, I think all of you had optics course during your BSc or MSc. So you have heard about how your optical systems makes things difficult for you, right? What are the problems? For example, if you have a lens, okay, and you have a screen, and the rays of lights are coming, how will that look? Sorry, let's not say a lens. Let's say a hole. Okay, it's a cardboard with a circular hole. Okay, and you have fringes. Why does that fringes happen? Diffraction, right? Yeah. So the same thing happens. If you design a coronagraph, you will also have diffractions. So your diffraction rings will come around the coronagraph image. You cannot have those diffraction rings because if your image is like this, your coronagraph image is like this, you have your blocked disk here, then you will have your concentric diffraction rings like this. So if your CME is happening somewhere here, you wouldn't be able to figure out the CME leading edge. So there were many other problems. One of the things that Lloyd also did is here, as the peripheral rays are coming, he put another Lloyd stop, okay, which will stop the paraxial rays, okay, because those are the ones which creates more problems, the scattered rays, okay. So once you do that, your life is way more easier. One interesting anecdote is that, to reduce the scattering of the lens surface, you need to lubricate the lens. So Mr. Lloyd, who designed the coronagraph for the first time, he did not have anything in front of his hands, what he wanted to use for lubricant. So what he used is his nose oil. So that's in the history books. Yeah. So once you do that, let's say that we have a coronagraph disk, and this is something how it looks. So this is the occulter. We call it as the occulter because this is something which will block the disk of the sun. So this is your basically artificial moon. So your moon blocks the solar eclipse blocks the sun for a natural solar eclipse. We have the occulter which creates an artificial solar eclipse. What is this dark strand? Anyone? Like a guess? Sorry? Correct. So it's just the holder which is holding the occulter. It's the shadow of that holder. Okay, just simple. So we have a name for that as well. We love giving names. So it's called as the pylon. Okay. Now, the thing is, once you have the CME observed in the coronagraph image, the question is that enough for us to go ahead? So the main problem is that this is the occulter again, right? So you have blocked out the disk. But unfortunately, as you block out, you're also removing some of the information, right? So you don't know what is happening on the disk of the sun. Okay, all you know is the solar atmosphere, and there is this explosion, big explosion happening. So this missing information is causing you a lot of trouble. What sort of trouble? So first thing that you don't know is that you don't have information about the birthplace of the CME. So on the disk of the sun, where exactly is the CME happening, or where did it take place? And the second question is that when did it take place? At what time did the CME start? So that's the first task that every solar astronomers do, is to find the birthplace of a CME. And how to do that? Well, you use a disk image. Okay. So you plug in a disk image. I think so. You have been seeing this disk image, right? So these are extreme ultraviolet observations of the solar corona. Okay. So you plug in a disk image along with the coronagraph image, and you stack those images to create a movie. Okay. So once you have a movie, you can play the movie backwards. Okay. And now, based on this difference of heights, you can always associate a unique disk phenomena with a coronagraph phenomenon. Okay. So it takes a lot of trial and error methods and a lot of experience. Let's not go into the details. So once you, let's say that you are able to identify a unique feature that is giving rise to the CME, you now have the birthplace. So you say that the CME is happening right here, it's starting here. And this small explosion that is happening here is looking at this, is looked as this beautiful three-part structure in the coronagraph image. Let me point out that it does not look as a three-part structure here. Remember? So this is not a white light image. So you don't have a three-part structure happening here, but you do have that in the white light observations in the coronagraph, right? So now, what is the good thing about that? So once you have the source location, what is the extra bit of information you understand? So anyone? So it says that the CME, is the CME traveling towards us or away from us? Are you able to say that from this image? Anyone? So how do you say? Let's say I draw a sun here, and I draw a CME like this. Sorry?
It is to be at some angle from this.
Correct. So what angle will determine that? Yes. So basically, the thing is, if you identify a feature on the disk, you can get the latitude and the longitude of that position, right? With respect to the solar disk. So you have your equator, you have your parallels of latitude, you have your parallels of longitude. So you have your location at the intersection of any two vertical lines. So let's say I give you the latitude and longitude of a source location. Okay. Now, would you be able to tell me if the CME is traveling towards the Earth or not? So mind you that the image is taken along the sun line. Okay. So from the latitude and longitude, which one will give you idea? Longitude, right? Correct. But even the problem is that the longitude itself is not unique, because let's say that this disk image was not there. Okay. So if this disk image is not there and you see these eruptions happening, so you don't know whether the longitude is 20 degrees behind the limb or 20 degrees in front of the limb, right? Because you're observing a projected image. So that's how the first point of understanding the source location and the association of the CME to the birthplace is important, because it gives you the first sense that whether the CME is happening on the front side of the sun or is it happening at the back side of the sun. Okay. Now, once you identify that, this identified source region can be categorized into two broad classes. One is the flaring regions, which are called as the active regions. Okay. I think someone was asking a question about active regions. Okay. And the second one are called as the prominence eruptions. So the active regions are the highly energetic portions on the solar corona. The magnetic energy is much, much higher, and you have these flares happening with a violent release of energies throughout the electromagnetic spectrum, starting from your gamma rays to the radio waves. And these are the ones in the quiet sun regions. Now, although these used to be called as the quiet sun region, but apparently now we understand there are also a lot of activities happening in the quiet sun regions as well. And you have these loop-like features. These are hanging features, right? So these are called as prominences. And these prominences erupt. As you can see here, this is a prominence, which is erupting like this, right? Also, people had people tried to initially understand that how is the CME located with respect to the source location, and people did some very preliminary works in the earlier days where they tried to understand that if this is a rough geometry of the CME, and if you try to draw two tangents, and let's say this is where your flare location happens, this cross. So this is the CME extended structure, and they wanted to see that how distributed the CME is. And what they found out is that if you have a parameter called as alpha, and you define your parameter like this, then if you see this equation, your A and B is here, and your C is here. So you can see that if alpha is 0, you will imply that this cross will come at here. So what does that tell you? It will tell you that if you have a source location and with the alpha as 0, then that would tell you that the CME is expected to be located at one of the legs. Okay, so one of the legs of the CME will be directly on top of the source location. Now, these people studied some CMEs and they found that there is a big histogram right for the alpha values from 0 to 0.1, and they were very happy to conclude that the CMEs are more expected to have their legs on the source location. But now that we have a lot of extra bit of information, very good instruments with respect to the earlier days, so we did some extended calculations, and now people understand that you have a very wide spread. So it's neither of the legs are expected to be on the source locations. It has a wide spread, and those spread of the CMEs are indeed different for the CMEs coming from white sun regions and the active sun regions. Second thing is, again, as I was saying, since you know the birthplace, it is also extremely important to know the birth time. So at what time the eruption happened here? Because this will tell you at the starting time of the CME. Now, how to do that? It's a little more tricky than the birthplace. The reason for that is this black region. Why is this black? Coronagraph, right? So it's the occulter. So you don't have any observations here. Your observation starts from here. This height is around 2 solar radii. Your solar disk is here. This is 1 solar radii. So 1 to 2 solar radii, you don't know what is happening. Okay? You don't have observations. So what you can do is to sample this observational gap. Now, how can you sample the observational gap? To do that, you need to have the CME trajectory. So you have to have the CME height time trajectory. Let's say I give you a CME height time trajectory like this. So you have a CME height for all different times. Now, since you don't have observations at the lower heights, you see that there are very less data points here. But what we want to know is what happens when the CME was exactly at 1 solar radii. What was that time? So how do we do that? Anyone? Okay, and then what polynomial? Sorry? Perfect. Yes, correct. So that's one of the ways, that's one of the simplest ways, very nice. So you have your trajectory, right? So what you can do is you sample your initial data points, which was near 2 solar radii. So when the CME just entered into the coronagraph field of view, you take 2-3 observations, track the CMEs, and get the instantaneous speed. Now, based on the instantaneous speed, as he pointed out, just assume that CME is following a polynomial profile. It can be a quadratic profile, it can be a linear profile. Just assume some profile. Let's not make our lives too complicated. And based on that profile, once you fit that profile to the height time data, you have your coefficients, right? Now you use your instantaneous speed to revert back with the same polynomial equation and extrapolate the expected position of the CME at that particular height, which is 1 solar radii, right? So that will give you the time at which the CME started. But then there is a problem. Can anyone say what can be that problem? The inferred height that you will get from the polynomial will be largely dictated by the choice of your polynomial, right? So if you have a quadratic polynomial, what does that tell you? If your height time is a quadratic polynomial, what happens to the acceleration? It's a second order derivative, right? So what happens to the acceleration? Constant. So you are assuming that at this lower heights, the CME is experiencing a constant acceleration. Now, if that is true or not, we'll come to know. Secondly, what happens if you take a linear profile? You say that there is no acceleration at all. So these are drastic assumptions. Okay. Now, the main problem of associating the temporal association of CME is that it's important because to predict the CMEs, the first thing that you need is to know the birth time and the birthplace of the CMEs. And the main problem is that one that I was talking about is the shape of the trajectory, but the other problem is ignoring the spatial size of the CMEs. Okay, what does that mean? So this is the coronagraph disk, right? This is where your observation is starting. You want to know the information here, and this is the shape of the CME. Now, when we study classical mechanics, you will remember that we treat every object as a point object, right? But the CME is not a point object. It has a spatial extent. So when you say that height is where, so what do you mean? What height? Height at which angle? Or height of which feature? Now, the answer that you might ask, the answer is that it depends on your science goal, right? So if you want to know that when will the CME arrive, then your point of interest will be somewhere at the leading edge. The point which will be traveling with the fastest speed, which will be leading the rest of the CME part. So you will say that, okay, let us assume that all the mass of the CME is concentrated at that single point, and we will track it accordingly. Okay. Now, this question comes that when does the CME erupt? So, does anyone have a rubber band? Yeah. वो नॉर्मल वाला नहीं है क्या? अच्छा नहीं नहीं इसने हुआ. Anyway, let's say that this is a flux tube. Okay, this is an array of magnetic field lines. Now, how does a flux tube become a flux rope? Anyone? Do you know the difference between a flux rope and a flux tube? Okay, I should have cleared it before I drew that image. So, a flux tube is a collection of magnetic field lines, right? A concentrated magnetic, a bundle of magnetic field lines. It becomes a flux rope when it gets twisted. Okay, that's what gives it the helical shape. Okay, now let's say that this is a flux rope. So you have this helical structure, right? As you see here, this flux tube is rising because of buoyancy. Okay, and now due to the foot point motions, they will experience some twist. Okay? As they experience the twist, they come near each other. When will they come near each other?
The twist is moved. The twist is a little more than.
Well, not exactly, but yeah. So it will depend also on the diffusion time scales. Okay. So let's say that the diffusion is also happening in the center. Okay, so you haven't done any course on plasma physics, right? Sorry. So let's say that this is a flux rope and it gets twisted. Okay. And due to the twisting motion, the foot points are also getting sheared. So due to this shearing, they will come near each other. And as it goes, imagine that this is a rubber band. Okay. So what will the rubber band bring in? An extra quantity? Tension. Correct? Yes. So the tension will try to pull it. And as soon as the tension starts pulling it, this central region will come near each other. And as you can see here, these are oppositely directed. So they will reconnect. Right? So you'll have something called as a magnetic reconnection in the flux rope, and a part of the flux rope will erupt. So this is usually seen as the CME in the corona. Now let's go to some of the CME properties quickly. I have some interesting stuff after this. Let's look at a very vague picture of how the speeds of the CMEs change. So if you try to plot a distribution of the CME speeds, you'll see that the speeds can range from a few hundreds to like 2,000 to 3,000 kilo. This is an old plot. So it's like 3,000. Now we have even higher numbers. So you can see that it can range from a few hundreds to a few thousands of kilometers per second. Now look at this picture. It is again a distribution of the speeds. But look at this part. It says that W is greater than equals to 30 degrees. So W is the width of the CME. Okay. So now what they've done is they have filtered a bit. So they have said that we will take only those CMEs which are wider than a certain number. So as you go to a relatively wider CMEs, the average speed increases. So can you infer anything from that? So what does that tell you? So if I go towards higher width, the average speed is also tending to be higher. So it tells you I didn't get you. Can you come again? Yes. Interaction with space weather. Solar wind, yes.
Hindering the speed.
No, if that was the case, then this speed will be lesser, right? So, no. See, this is 466, this is 470, right? Getting more. So it tells you that the width and the speed has got a connection. So probably it feels like the wider CMEs might be faster. I think someone was asking about speed. You were asking. So here we are that people found out that if you plot two distributions of speeds and you filter one of the distributions based on the width of the CMEs, you get an apparent indication that probably the wider CMEs might be faster. So to understand that better, you can see that if you plot a distribution of the width of the CMEs, Now, let's say we separate the CMEs into slow and fast. Okay, let's say that we call CMEs as slow when they are lesser than a certain speed, and we'll call them as fast when they're higher than a certain cutoff. Okay, so once we segregate them into slow and fast, and you plot a distribution, when I say a distribution, it's a frequency distribution. Okay, so you have the number of events here, you have your width on the x-axis, and you see that they follow two different power laws. Now, there is a special property of power law. What is that? Power laws? Sorry? So let's say I have a quantity x, okay? And I say that the quantity varies as x to the power alpha. F of x equals to x to the power alpha, c into x to the power alpha. So do you have any advantage of that sort of formulation in physics? What does that tell? What does this equation tell you? That irrespective of x, the f will change in same way. So scale invariance, what we call a scale invariance, right? So if you have, let's say this alpha is minus 3.8. So every number will follow the same profile, right? That's what power laws gives us a window of advantage. So it tells us that it is scale invariant. Now, how is this information getting communicated to this plot? Let's understand. So let's say we take a particular width cut here, okay? We take a parallel line from here. What does that tell you? That the higher the width, it is more probable to get a fast CME than a slow CME. From this plot, just to draw an imaginary straight line. So the slow CME will cut somewhere here, right? And the fast CME will cut somewhere here. Mind, this is a logarithmic scale, so it's condensed, okay? So it tells you that indeed, the probability of expecting a CME with a wider angle will be if the CME is faster, right? That tells you because the power laws in the width distributions of the CMEs are different for slow and fast CMEs. The slow CMEs are following a steeper power law. So it tells you that if you increase the width, the number of CMEs that you can expect for slow CMEs will decay faster than the fast CMEs, right? Again, so I think Gopala talked about solar cycle, right? So you know that the solar activity varies, right, in an 11-year period. So even the CMEs also mimic that, because some of the CMEs are coming from the active sun regions, some of them are coming from the quiet sun regions. So if you try to measure the number of CMEs that happens each day, you will see that during the solar minimum, the number of CMEs can happen from 4 to 5 CMEs each day. So you can understand that how important it is to have a very clear understanding of the CMEs, because right now, we are in the rising phase of the cycle. Okay, so the number of active regions is increasing every day on the disk. So more and more CMEs are expected to happen, and you don't know which one will be geo-effective. The other interesting part is if you are going to try to follow the occurrence of the slow and fast CMEs with respect to the solar cycle, the interesting part is you see the blue one is for the slow CMEs and the fast ones are in black. The red curve is for the sunspots. So you know the sunspots, right? So you measure the sunspots, they give you the international sunspots number. So you plot the sunspot number and they are expected to show you the solar cycle variation. But I mean, strangely, the blue curve overshoots the sunspot curve. So any inference from that? So you know that sunspots are one of the sources of CMEs, right? There are active regions that are rooted on sunspots. The active regions are high up on the corona, the sunspots are on the photosphere, right? I mean, by definition, we say that sunspots in the photosphere, okay? It's the same magnetic structure. So what does that tell you? That this gap between the occurrence of slow CMEs and the occurrence of sunspots, although the sunspots are much lesser, you see that the number of CMEs is shooting up. So it tells you that there has to be a source for the slow CMEs, which are not the sunspots, right? So irrespective of the fact that you have sunspots or not, you can expect a healthy number of CMEs happening on the solar corona. And that's what made the space weather scientists very curious that, people used to call that in the solar minima, the sun is really quiet, but it's really not that. So you see the slow CMEs are shooting up, and it's not really quiet. The corona is really active. Now, this is an interesting part. So the CMEs expand. I was talking about the CMEs width, right? So if you see this particular image, so if you get along with time, you will see that if you measure the width of the CME like this, I was saying that you draw two tangents, right? And you measure the angle subtended by the two tangents. So this angle keeps on increasing. And if you try to understand that how the width changes, you will see that initially this is the height, and this is the width. So this width will initially increase and then become saturated. Okay, so it tells you that the CME attains a constant width after a certain height, but initially the width increases. Okay, if that is the case, then what is the weirdness in that? So we human beings, we grow up something like this. So there is a baby boy, and then it grows up like this. Okay? But unfortunately, if we had been like CMEs, then we would have grown up something like this. So any difference that you see in these two pictures? What is the difference between growing up like this and growing up like this? You grow fatter, right? Okay, so you're expanding. So the tricky part is the CME has a strange law, and they're expected that they will follow this law. Okay? So what is that law? That law is called as self-similarity. What does that self-similarity tell you? It tells you that if, let's say this is a cartoon of the CME, right? So this will be the height of the leading edge. So the law of self-similarity tells the CME that when you are evolving, your height is increasing. But I'm not happy with that. As long as you keep on increasing your height, you have to also expand. Because as this distance is increasing, this cross-section, you can see that this is like a toroid, right? It's like a cylinder. So the cross-section will be a circle. So the law of self-similarity tells that if the height of the CME is increasing, then the cross-section radius of this toroid should also increase. So it will expand like a fatter and fatter sphere. So if the CME grows, it will also be bigger. It would not just grow in height. And why is this important? Just let's say that the CME is coming near Earth. Now think about it. Why is the expansion important? Yes. So this is the Earth, not to scale, and this is the Sun. So a CME is like this. Okay, it has come all the distance from the Sun to the Earth, and accordingly, this is a good CME, so it plays by the rules. So it has expanded. Now, if the law of self-similarity was not there, how would the CME look? It would look somewhat like this, right? Right? It would just expand with this height. So it will not disturb us. It will just glance beside Earth, and we would not bother. So we would only bother if the CME is absolutely head-on with us. But unfortunately, the CMEs are also expanding in the interplanetary space. And that's what makes it that there can be a glancing collision with the Earth. So that's what we are trying to figure out, that if there is a glancing collision, what will be the magnetic orientation at the point at which the glance happens? Yeah?
As CME expands,
Yes.
then the magnetic fields are located at the source region.
Yes.
Sometimes there will be that magnetic field that detached from that. Is there any possibility that?
Good question. So, okay, let me see if I can get the answer from. So, you know that there are two legs of the CME, right? Okay. So, let's say that one of the legs gets detached. What can be the implication? Let's say it gets detached. Okay. After that, anything with the kinematics? Correct. What you are saying? It will rotate, not twist it. So there will be a torque generated. Initially, it is a force, right? Why is it a force? Because your Sun is like this, and your CME is rooted like this. So this is the first leg, this is the second leg. Okay. Now let's say this foot point gets disconnected. How will it look? It will look something like this. So the force that was leading to translation will now have a force arm with respect to the center of force. What will that make? The force will get converted to a torque, right? This torque will impart an angular momentum to the CME. So what will happen? The CME will start rotating like this. And why is that important? Any idea? Why is the rotation of a CME important? What will change if a CME rotated? Think in that way.
The impact area.
Sorry?
नीचे भी ऊपर भी दोनों साइड इम्पैक्ट रहेगा।
तो Anyone? What? Sorry? So what is changing if a CM is rotated? Think in that way. What orientation of what? No. You're going in the right direction. Orientation of what? What is the CME made of? What is it made of? Plasma and magnetic field, right? So the orientation of the magnetic field will change, right? So you have your magnetic field directions like this. So now this has rotated. So this will now become like this. Okay. So our earth is here. So the earth magnetic field is like this, right? So initially the CME was supposed to hit like this, but after rotating, it has become like this, and the direction is now like this. So initially the CME was not geoeffective. It was not supposed to create a geomagnetic storm. But now, just because one of the points has got disconnected, it has now started rotating, and we don't know. Now we have to model the rotation rate of the CME and predict that when it arrives at the earth, what will be the orientation, right? Yeah. So based on this, a very easy way to understand how cell similarity works is that you have this radius, which is from the center of the sun, and you have A as the cross section. So all it says is that if A is equals to KR, then K should remain constant with time. That's all it tells you in terms of mathematics. It's a very small equation, but it has profound consequences on the life of a CME. So again, as I said, that the CMEs grow fat, but it's weird. How is that? Now, if you try to model the different parts of a CME, we have found out that the volume of the initial head of the CME and the legs of the CME expand at different rates. Let's say we eat food, okay? So when we eat too much of junk food, we get belly fat, right? So it happens different for the CMEs. So the junk food that the CMEs get is Lorentz force, right? So that's the only food for the CMEs. Okay, so they get injected with Lorentz force, and based on the Lorentz force, they will expand. Now, for every CMEs, this is valid that the head of the CMEs, the middle part of the CMEs, and the legs of the CMEs are expanding at different rates. In fact, the head of the CME is expanding much faster, and the legs are expanding at way more slower rate. So what does that make the CME look like? Like this. So the legs will be narrow, but they will be rooted at the sun. Their head will be way more fatter than their body. Yeah. So this is again another weird feature of CME evolution, and this makes calculations complicated. Now let's quickly talk about some interesting parts of CME kinematics. So as long as we say kinematics, so there is a difference between kinematics and dynamics, right? So kinematics gives you the idea that you don't have to deal with the complex mathematical calculations of the forces, right? You just go ad hoc. So we will keep this part of the talk ad hoc. So let's say that we understand that the kinematics of the CME is an outcome of three forces. As I had said, the Lorentz force will always be there because there is magnetic field in plasma. So what is the Lorentz force equation? Yeah, J cross B, right? So you have J cross B. Of course, you will have gravitational force. And the third is the drag force. I think someone pointed it out earlier in the talk. So the CME is expanding through the solar wind medium. So the solar wind is flowing outwards with a constant speed, right? Yeah. So if you remember that the problem in Irodov problems in general physics, the first problem that gives you in that book, the first problem, first chapter, is a boat crossing a stream of river, right? So the river has a speed, and the boat has a certain speed. So now you have to model the relative speed and determine at what point and in which place you will be reaching with your boat. So the same happens with the CME as well. The CME is traveling with some speed V1. The solar wind is traveling with the speed V2. Usually, V2 is lesser than V1. But sometimes V2 is again greater than V1. The solar wind is faster than the CME. So based on that, the CME experiences a drag. Now when I say drag, our initial intuition is that it drags you backwards. But in reality, for astrophysical plasma, it's not like that. The drag can happen both ways. Because the drag depends on the difference in velocities. So if your velocity is lesser than the ambient velocity, the drag will accelerate you. Okay? If it is higher, then the drag will decelerate you. Same thing happens for the CME, and based on the interplay of these three forces, the CME shows this beautiful three-phase profile in its kinematic plot. So if you plot the velocity of a CME, it shows three features. So you have the first feature, where you have a slow rise, the velocity is increasing very slowly. Then you have the second part, where this blue curve, if you see here, the velocity is shooting up in a very short interval of time. What does that tell you? That the CME is experiencing acceleration. And that acceleration is way higher than what it experienced here, because the rising speed was very small. Now the rising speed is higher. And then the third phase comes, where the speed is almost constant. So does that mean that there is no force here? Anyone? If the speed is constant, does that mean that there is no force?
Force is there, but there will be equilibrium.
Correct. So Newton's first law tells that it will propagate in the same way. So it does not mean that the force is not there. The resultant force is zero, right? So all the forces, they balance out, the Lorentz force and the drag force. थोड़ा सा यहाँ पे धक्का होता है, यहाँ पे वो constant हो जाएगा, ठीक है? So in real life, if you plot it, this was a cartoon, but in real life it looks like this. And this is the region where you see this is the acceleration plot derived from the velocity plot. See how it looks. So initially we were talking about first order and second order profiles, right? First order and second order polynomials. So you can see that neither of them are true. So the acceleration is shooting up like exponential here, and then again falling back. And then the acceleration is almost zero here. So it tells you that how important it is to not to use any ad hoc assumptions on the CME profile. Okay? I think I'll skip this part. Well, this is an interesting part. So there's a strange thing about CMEs. Again, if you plot the acceleration magnitude of the CMEs with respect to the acceleration duration, so there is a duration for which the CME experiences the acceleration, right? You saw the acceleration plot. After a certain time, the acceleration becomes zero. So there is acceleration duration, and there is a magnitude that the CME experiences. So if you plot one against the other, you get an anti-correlation. So what does that tell you? The higher the acceleration magnitude, lesser is the duration it is experienced for. So if a CME is experiencing a high acceleration, it will experience it for a shorter time. But if it is experiencing a smaller acceleration, it will experience for a longer time. And this strange behavior is seen in the velocity profiles of the CMEs. Look at this profile. It is experiencing a very high acceleration, but then the profile is becoming constant. Right? What happens here? The velocity is constantly shooting up. So this is a CME which is located somewhere here. The acceleration magnitude is low, but it is experiencing for a longer duration of time. Why is this important? Because if you're trying to predict the arrival time of these CMEs at any planet, you have to consider these profiles. If you are assuming that the speed is constant, then you will say that the CME will hit a particular planet, let's say Mercury, at 6 p.m. But in fact, the CME has already passed at 3 p.m. because you ignored the acceleration. So this is a special class of events. These are called as the halo CMEs. Why are they called halos? Because of the name. So what does a halo tell you? It's like it comes from that divine halo structure where people used to say that, you know, the pictures of gods, they have this halo behind their head, right? So it's the same way a CME is seen around the equator. It is seen like a circular halo. So any guesses? Because this CME is traveling towards the line of sight. So it is looking like a circular ring, right? Why are they important? Because they are traveling towards us. Now, how do you distinguish if the CME is traveling exactly towards us or away from us? How do we distinguish? What information do you need? Okay. Let's say we don't have Dopplerograms. See, I told you in the initial part of the talk, right? If you have a disk image and you have a source activity on the disk, if you're able to associate that, you'll say that it is happening on the front side of the sun. So it is traveling towards me. Because only the coronagraph won't be able to tell you that if this halo is towards me or away from me. Right? That's why we again need disk observations to be complemented with the coronagraph observations. Yeah. Now, the other strange part is that the viewing perspectives matter, because if you see the same CME, which is looking like a halo from a particular line of sight, will not look halo from a different line of sight. So these are two spacecrafts given by stereo. It's a mission by NASA, which gives two spacecrafts traveling at two Keplerian orbits, and they're circulating against the sun, and they're imaging the CME from two different vantage points in space. So you'll see that they're looking completely different. And if you see this image, you'll see that this is the same CME. Okay. Now this is how real life CMEs look. Not all CMEs are as beautiful as I showed in the introduction slides. Okay. So from two different vantage points taken at the same time, you see that the CMEs are looking completely different. So if I give one image to you and one image to you, both of you will measure two different heights at the same time, right? So the question is, which one is the correct one? And if you track based on this particular image, if you plot the height time plot and you fit it with a straight line, you'll get a completely different speed, right? So your space weather predictions will be hampered. So this is something called as the projection effects, right? Now, what is the solution? The solution is that we do 3D reconstructions. How do you do that? So if you remember, I said that these images are taken from Thomson scattering, right? And what Thomson scattering imparts is polarization. So this polarization information is used to extract the 3D structure of the emitted electrons. Once you do that, you can generate a 3D structure of the CME based on multiple vantage point images. It's the same thing that happens in our eyes. Just take two fingers like this and close one of your eyes. You will not be able to figure out the distance between the two fingers because one of the dimensions is lost. Our brain does this 3D reconstructions all the time, right? Okay, this is, I think this is the last part here. So the other part that I was supposed to talk about is the shocks that CMEs create. So this is again a very important part because this is the one that determines the geoeffectiveness of a CME, whether the CME will create a storm at Earth. And if you see, when your eyes get enough framed, you see this is the leading edge, right? Now, if you see, there is this fuzzy structure here, a dense fuzzy structure just ahead of the leading edge. So this is considered as the shock. And we call it as the white light shock. Why do we call that so? Because it is identified in the white light image. So we say that this is the white light shock generated by the CME. So if the CME is faster than the local Alpine speed, then the CME will generate a shock, right? So this shock will produce radio emissions. And those radio emissions look like this drifting features. So with time, the frequency will reduce, okay? Let's not go into the details, but these radio emissions are very handy. Why is so? Because if you capture the radio emissions, the frequency at which the radio emission started gives you an idea at which the shock formed, the height at which the shock formed. And this is important because if you know the height at which the shock formed, you will know that that was the time at which the speed crossed the Alpine speed. And that tells you a lot about the ambient medium at that particular instant. So why is it crucial? It's crucial because we were talking about the CME leading edge all the time, but it turns out that it's not just the nose of the CME which is important. So if this is a CME, then we say that this is the nose, okay? And these are the legs, right? So in one particular work, it was found out that if you track the CME and the CME legs, it was seen that the nose of the CME is traveling fastest. Just see this coronograph image. This is leading, right? So if you track it, you will find that the speed at this point is higher than the speed at this point, or the speed at this point. So that's again another crucial difference between a rigid body and a non-rigid body. So when you track a rigid body, every part of the rigid body travels with the same speed. But that does not happen for a CME. Okay. Now, if this is traveling at the highest speed, you would expect this point to create a shock, right? So what we did is, we looked at the radio data, yeah? And what we found was that the radio contours was located at the flank of the CME. So it told us that it is one of the legs of the CME which produced a shock, which created a type 2 burst, I mean the radio burst, okay? So it tells you that why is the radio data important? It is important because the white light is not sufficient to tell you that which one is effective to create a shock which will give rise to a radio emission. And these radio emissions are important because it will help you to track the shock, irrespective of whether it is visible in the white light image. Because if you remember, the shock is very fuzzy, right? So it won't be even possible after 1 or 2 frames to identify the shock in the white light image. Or even I will say that this is the edge of the shock, you will say that this one is the edge. There will be discrepancy of that as well. But the radio data gives you more information and with more confidence that if you have the radio transient drift of the burst, you will be able to track the shock with different heights. And that will tell you that whether the CME is able to generate a shock when it reaches a planetary atmosphere. Okay? So now the last part is that what are the things that we are looking up to? So as far as CME science is concerned, we have 3 big questions. First, when will a CME occur? What do I mean by that? Are we able to predict if an eruption will happen? I will give you a disk image. Now you do the analysis and you tell me that if there is an active region, can I expect a CME to happen? Or if there is a prominence, can I expect that prominence to erupt? Or is there a stable prominence? Or is there an instability? The second question is, when will a CME arrive? So this work is being done for the last few decades. Although we have arrived at a much considerable improved position, yet we do need to do a lot more. So the predictions that we do right now, they have an error bar of some few tens of hours. So that's too much, all right? And the problem happens mostly for slow CMEs. So we have to give the predictions well ahead so that, all the low Earth orbit satellites can be turned off just to reduce the damage if there is a CME heading towards us. So this is important. And the third and the most important part is what will be the magnetic structure when the CME comes. And all these are now being done with different groups. People have been using machine learning techniques, artificial intelligence, and other analysis tools to predict if a CME will arrive at Earth. If they do arrive, what will be the orientation of the CME? How will the CME look? What will be the energetics, etc. So with that, thank you for listening. And I hope some of you contribute these questions.
Aditya-L1 is going to have a coronavirus.
Yeah.
But how well is it prepared to track the CMEs which are coming towards the end?
Oh, it's sorry, I did not include much slides on that. Quite well prepared, actually. So let's say this is the sun. Okay. Now the coronagraphs that I was showing you, they are somewhat like this. Okay. So this is the field of view of the coronagraph. So let's say this is 2 solar radii. Okay. So the Aditya coronagraph that we have, it will start somewhere here. That's very close to the sun, like 1.05, 1.03 solar radii. So let's say 1.1 solar radii for safe sake. Yeah. Now, as you were asking about Earth-directed CMEs, right? So the problem is, if you just have the coronagraph, the Aditya field of view is till here, 1.1 solar radii. So within this, if you see a CME, you cannot say whether it is traveling towards us or not. It's not sufficient. So you need a disk observation. Now, thanks to the Aditya machine, we have another payload called as a suit. Yeah. So suit will provide you this information. It will observe the disk of the sun at different wavelengths. So you will to see the potential activities, the prominences, and then use those data and predict. And if you have a source activity happening on the source data, you can say that activity is happening on the front side of the sun. And that's how you can guess if the CME is traveling towards us or not. Yeah.
Sir, yes, sir. Coming to determining the trajectory of CME, we should also need to take in account the rotation of sun, because that is follows in co-rotating interaction region. As the sun rotates, the CME gets swirled to the opposite direction.
So what is your point? To include the co-rotating interacting regions or the rotation of the sun?
So yes, we need to take that variable as well.
Yeah, you're correct. So the good thing is the co-rotating interaction regions it happens along a plane. All right. So what are the CIRs? Are you aware of the CIRs?
No, I'm actually new.
Okay, you are asking.
I just have overview.
Acha. Yeah. So the CIRs are, so you have your solar wind streams, right? So you have a fast stream, you have a slow stream, and those streams are catches up with each other, and the sun is also rotating, right? So these solar wind streams will look like this, right? So these are the co-rotating interaction regions, and the fast stream will catch up with the slow streams. I'm talking about the solar wind, not the CMEs, right? And then there will be CME like this. Okay. So what he is pointing out, it's an important parameter. So when the CME is coming here, the CME will interact with the CIR. Now, this is important because an interaction of the CME with the CIR leads to mass depletion. So where will the depletion happen? You have the flux rope like this. You have the accumulated mass on top of the flux rope. So once you have the CIR here, you have a CME here. Okay. This mass will get depleted, and the leading front, which was very spherical initially, this leading front after a certain time will look like this. Yeah. So your point of impact might change. Your leading edge was somewhere here, now the leading edge is here. Yeah.
And sir, yes, coming to that, is CME burst is associated with solar flares?
CME burst with radio.
No, sorry, not CME burst, sorry. Like every CME event is associated with solar flares.
Yes. Okay. So that is not all CMEs comes from solar flares. There are non-flare regions, which I showed at some point of my talk, that there are quite some regions where there is no flares as such. But again, it depends on how you define a flare. People nowadays say that even the quiet sun regions do have nano flares in that way. But the so-called high energetic flares, they create some CME. But you also have flares without CME. And you also have CMEs without flares. So there are three classes: CMEs with flares, flares without CMEs, and CMEs without flares. Okay. So now what we try to explain it is that it is part of a single unified picture, that it is a magnetic instability, which leads to a flare. And based on the energy budget and the coronal structures, the magnetic morphology, it will dictate whether that will give rise to a CME or not. So it is not sure that if you have a flare, you will also have a CME. Yeah?
The last question. Sir, there is a debate about that coherent structure of CME. Some say that it is coherent, some say it is not coherent.
He has the constant. Nice. So, yeah, that is a debate.
Because I read a paper where they say the coherence can be argued, the argument can all towards the coherence up to at least 1
Yeah. So the topic of coherence really comes at a very longer distance, as I was showing you the self-similar expansion profile. So once the self-similarity starts, which happens, let's say for some CMEs beyond 20-30 solar radii, okay? So you reach around 50 solar radii, your self-similarity becomes almost constant. So then you can expect that the coherence inside the CME flux rope might be valid. Okay? The coherence times. Yeah.
Thank you, sir.
Yeah.
On a very similar note, but on a very lower level.
No, there is no level.
The difference between, I know a very vague definition of the difference between a solar flare and a CME, but maybe it would be good.
Achha. Standard flare CME model? Achha. So, a flare by definition, we define it as we have something. When you go back, I would recommend you to read the CSHKP. This is a standard flare model. So this gives you a very good idea how a flare and a CME is different from each other, at the same time how they're connected. Okay, so you have a magnetic field configuration, something like this, and you have your reconnection happening here. Yeah. So initially, there is a flux rope formation on the sun. You have your strapping fields. Yeah. Then there is a reconnection at the bottom. Okay. So now it depends on the absolute magnetic morphology that this CME that I am showing, it is a mass motion. By name itself, it is CME, coronal mass ejection. And flares, by principle, does not include mass motion. It is an electromagnetic emission.
There is no plasma or something else.
No, there is no mass motion of plasma outside. So the magnetic field lines reconnect. So let's say here is an active region. Okay. So there will be coronal loops, big loops. And then there can be a reconnection. So these loops will become very bright. Okay. And they will create a lot of emission. These emissions will be starting from the radio waves initially, which will come from the foot points. Then there will be hard X-ray emissions, soft X-ray emissions. So by definition, flares are electromagnetic emissions, which generate emissions across the spectrum from radio waves to the gamma rays. But CMEs are the mass motions. So if the flares are really energetic, then it is more probable that we will have a CME along with that flare. But we do also have very energetic flares without a CME. Okay.
So there is like no association, no concrete association that a flare will generate a CME or CME.
Okay, so I think I skipped that part of the slide. I should have covered it. So there is some association. Let's say that this is the number of CME, okay, and this is the duration of flares. Okay, the duration at till which the flare continues, the emission continues in the spectrum. So it turns out that the curve is like this. So the more the duration of the flare, the more probable it is to get a CME out of it. Right. So that's one of the associations. There are other as well. There are associations that the larger the flare, the more compact the magnetic structure, the more it is probable that the CME will come out of it. But then there are other things like failed eruptions and all. Yeah.
The animation that you showed, where that after magnetic reconnection,
Yes.
that magnetic field detach and propagate to the Earth. So after it being reaching near to the Earth,
Yes.
there will be a shock shelf field that will.
Yes.
So what is that shock shelf field? I didn't understand that.
Shock shelf.
Shock shelf field, sheath field actually.
Yeah. So I was talking about three-part structure CMEs, right? So the leading edge, the cavity, and the core. So when it comes to the shock structure for the fast CMEs, the three-part structure changes to a five-part structure. So you have your flux loop like this. You have your leading edge here. You have your core here. Yeah. Now comes the five-part structure where you have your, if the CME is fast, I mean faster than the Alpine speed, then it will generate a shock. Okay. So this will be the, let's say this is the shock envelope. Okay. This distance between the shock envelope and the leading edge of the CME, this part, this is called as the sheath region. And this sheath region is important because the more the sheath region, the more powerful the shock is. So the extent or the width of the sheath region will give you an estimate of how powerful the shock is, or how strong the shock is, whether the shock is strong enough to produce a radio emission. Yeah.
And this, because of the shock sheath field, there will be magnetic reconnection between Earth magnetic field and.
No, the reconnection is not due to the shock. It's due to the magnetic field inside the CME.
Inside the CME.
The shock is just a front, right?
Yes. I'm confused about whatever the magnetic field backed by the solar wind, that become BZ component.
The BZ that we are talking about is the BZ of the CME, not the solar wind.
Means magnetic reconnection between BZ of the CME and the Earth magnet.
Yes. So that BZ is because of the flux flow, the magnetic orientation, because that's what contains the magnetic field itself. The rest is plasma and void. Yeah.
And it is also affected when CME level. Then the magnetic field that dragged by the solar wind, that will be grabbed along the CME and it will be southward and that will.
No. That does not happen, but it's only the plasma that affects that. The magnetic field, it might get pushed apart, which happens really low in the corona, but once it is in the heliosphere, it's not like that. But I don't know if you have heard about something called as the switchbacks.
Magnetic switchback.
Yes. So this is something which is recently going out. So I mean, people are giving some explanations, but this is one of the magnetic interactions that is happening within the solar wind. Yeah.
So does every CME which comes into contact with our magnetic field result into a geometry?
No. So there are certain conditions. The first condition is that you have to have a magnetic reconnection. And to have a reconnection, the magnetic field has to be anti-aligned. So when the CME arrives at the Earth, the magnetic orientation of the CME has to be opposite to the Earth's magnetic field at that point. That's the first requirement. So once you have that, you are guaranteed to have a magnetic reconnection for a storm. for a geomagnetic storm, but then the severity of the storm will be dictated by some other parameters of the CMEs, like the RAM pressure, the plasma content, how energetic the CME was, what was the speed, etc.
If the magnetic field of the CME is at some angle with our magnetic
Yeah.
field, what will be the result if it's not a geomagnetic storm?
Yeah. So in that case, what happens is people have done this through simulations. So this is the Earth, and this is the Earth's magnetic field, and this is the Earth's magnetosphere. Okay. By magnetosphere, I mean the region till which the Earth's magnetic field is dominant.
Yes, sir.
Okay. So the CME front is coming like this. Now let's say that there is no reconnection because magnetic fields are along the same direction. But this will have a speed v, right? So this will cause a compression here.
Okay, sir.
So there will be a non-zero pressure difference. This pressure difference will cause a compression, and then there can be some high energy particles which were accelerated, which will pour into from the higher latitudes inside the solar Earth's atmosphere. That's all. But there will be a compression. And this compression will lead to different changes in the ionization scales, the pressure, the temperature, etc. The thermodynamics of the Earth's magnetosphere.
But not a geomagnetic.
Not a geomagnetic storm.
Can you tell me a little bit about the role of we studied about, I think, heliosysmology
Okay.
last class.
Yeah.
In terms of when will your CME around the sun?
Mhm.
I mean, I know that was a very vast question. It might take a whole lecture, but I mean, in terms of accuracy,
Mhm.
if we only look at the magnetic fields
Yeah.
of the sun,
Mhm.
predicting CMEs through that,
Mhm.
and using astrosysmology. I mean, is there? I don't know if the question is well.
No. I mean, there's nothing wrong with the question, but I have to think about it. I don't know. It's difficult. I don't know. People have.
Isn't been like explored in the.
No, heliosysmology has been explored and people relate it, but directly using heliosysmology for space weather prediction hasn't been done. I mean,
Not in terms of CMEs,
Yeah.
we read about some CMEs in stars during a public lecture, but then astrosysmology is mainly about it in this from the Doppler oscillation.
Yeah.
Then you try to probe the interior, right? Like you probe the interior of the sun. So I don't know the relation, but the CMEs that kind of relation.
You said that it was about heliosysmology. Was there a relation between coronal? It wasn't.
for coronal heating, please.
No?
Heliosysmology.
Okay. It was.
Okay.
So you showed that the slow CMEs,
Mhm.
they are not associated with sunspots.
Yeah.
So what are they associated with?
So I showed you about those hanging features, right? The prominences. Do you remember? It's like if this is the sun, then you have a structure like this, a hanging feature, which was erupting. So those are rooted in the quiet sun regions, and we call them as the quiescent prominences. So when they erupt, we call them as eruptive prominences. Okay. So these are the ones which are different from sunspots. So we have a very good number of CMEs which arises from these prominence eruptions, which are not associated with sunspots. So if you don't have sunspots, you can still have CMEs. That is a good question. So the first thing that you should ask is, I mean, how does a CME widen? Why does a CME widen at all? Why should the width increase? So as I said earlier, that when the CME erupts, it is injected with Lorentz force, right? So when you have Lorentz force, so this J cross B force, it can be taken into two components, okay? So J is curl of B, right? So curl of B cross B. So you can change this into two parts, okay? The parallel component, the perpendicular component, okay? Now, a part of that leads to the expansion of the CME, okay? And a part of that leads to the translation initially. Okay, and what was your question?
Why it is faster?
Why it is faster? Yeah, why wider at first? So you can expect that both the widening of the CME, both the expansion of the CME and the acceleration, both are controlled initially by the Lorentz force. So you can expect that if a CME is wider, it has more Lorentz force. That's why it will also be faster. So the Lorentz force is more. Yeah.
I read in a research paper that fast CME tends to deaccelerate and slow CME is accelerate. What is the reason?
Yeah, as I was saying, that it's based on the drag, right? So drag will depend on the relative velocity. If your velocity is faster than the solar wind will decelerate, drag you back. Just imagine that you are flowing through a river. So the river stream, if it is faster, if you have a thermocol with you, the stream will take you along. But if the flow is very slow and you are swimming against the flow, then you will try to resist the flow, right? So the same thing happens for fast CMEs. The fast CMEs are faster than the solar wind. So they experience deceleration. So after a certain acceleration time, the speed curve becomes flattened. Whereas the slow CMEs, they continuously experience an acceleration until they reach the solar wind speed, when the difference in speed becomes zero. So if the speed difference becomes zero, your drag force becomes zero. Your drag force is basically your Stokes law, which we read in fluid dynamics, right? So it's slightly modified for the plasma case, but it's basically the same concept.
Does planet play any role in this? Like
Planets?
the force of planets, gravitational force?
No, we are talking about the heliosphere. No planets is there here.
Hello, sir. We study about the connection of the leading edge with the Earth's magnetosphere. So, what will be the role of the plasma which is connected with the core while interacting with the Earth magnetosphere?
Yeah, that is again a good question. So that's why, again, analysis is important, because you have something called as, so what I showed you about the radio data, you saw the drifting features, right? So those are called as type 2 bursts. So we have something called as type 4 bursts. And so if you remember the radio spectra, you have frequency here, you have height here. So your type 2 burst looks like this, drifting like this, remember? You have something called as type 4 burst, which is looking like this. So these are the bursts which comes from plasma in a trapped magnetic environment. Now you can understand that the core of the CME. So if you remember the geometry, the magnetic geometry, it's like this. So the core is the inner part. So in local spatial scales, you can expect that it is a confined magnetic morphology. Yeah. So the plasma is confined there, it's trapped. So those trapped plasma often emit these type 4 bursts. And this plasma can sometimes lead to reconnection. Because, why is that so? Because you see that it's a helical structure, right? So it may so happen that the orientation of the leading edge was not geoeffective. With the bottom part, it might have a glancing encounter with the Earth's magnetic field, because it's a spherical blob. It's a 3D structure. It's not a 2D structure. It's not a plane that if it has gone past, it won't interact. So there is a spatial extent as well. So the core part also have a trapped plasma, and that is giving rise to as a type 4 burst, which will give you an idea that if that is important for the consideration as well. But yes, it can happen.
So the extent of the core will be same for the slow CME and fast CME? Or it will be extent of the core? What do you say?
Spatial extent.
Yeah.
Okay. So the core does not really change that much, but again, the spatial extent of the core changes due to two reasons. One reason is because of thermal expansion, because of the temperature of the core plasma, and the second is due to ionization. So there is hydrogen ionization, and due to that ionization, there will be more Lyman alpha emission, which will be recorded. If you have a Lyman alpha filter, you will see that the extension of the core is increasing. So this is seen again for faster CMEs to be happening more because they have more energy, and for the slower CMEs, the extent is expected to be lesser.
Thank you, sir.
I just want to release the question. The three parts of CME,
How do we know that all the three parts of CME reaching to the Earth? Is there any method that, yes, now leading edges come, then right?
Okay, yeah. So, to understand something, you have two ways to measure something. One is you go to that thing and touch it. Let's say I want to measure this structure at the temperature, I'll go and touch this structure. And the other is I'll wait here and I'll wait for it to come to me. Okay, so that's called as in situ measurements. So same thing happens for CMEs. So we have instruments in the space, so it waits till the CME will pass through that instrument. Okay, so in the same way, if we have a magnetometer, and if a CME is passing through that instrument, then your magnetic field will undergo a rotation like this. Why? Yeah, one of the, let's not say B, one of the three components will, at least one of the three components should undergo a rotation. And that is a clear evidence that the CMEs are indeed having a flux slope structure, which is helical. Because if it is a helical structure, then the direction of the field line is constantly changing. It is like this, like this, like this, like this, like this. So when it is passing through a single point where the instrument is located in space, so the instrument will constantly measure the numbers with different values. Ultimately, it will undergo change in sign. It will be positive, then zero, then negative, then again go back to positive, as the rotation of the entire helical structure is complete. So that gives you an evidence that the flux loop has passed. After that, there will be the cavity, right? So during the cavity, the magnetic field will drop. Because as I was saying, the magnetic field will be higher because it is magnetically dominated. Then the core will again come where you will have more emission, but the speed will be less. The core speed is lesser than the leading edge speed. So when you understand in situ properties of CMEs, you have a series of plots. You have your BX, Y, BZ, you have your pressure and temperature, then you have your speed of the CME. So when you align all these plots together, then you have clear idea that all the three structures of the CME has actually passed through you.
Sometimes we only can detect leading edge, sometimes we only can detect the core.
Yeah, but this detection, what you are saying, is only because of remote sensing observation, which I was talking in my talk. But that is not the whole picture. There is also a large amount of work that is going on based on in situ observations. Only when the CME is passing through me. And that is one of the probes which people receive for the first time, that we are talking about this magnetic flux loop. Is it really happening? So when you saw that rotation, people understood if it is really happening. Yeah.
So is there any correlation between the past CMEs and the new emerging CMEs?
So what sort of correlation?
Like when it will reach the Earth, or the features of how it will travel, or any?
Well, so there are something called as homologous CMEs. Okay, so from the same active region, there can be 2-3 CMEs. So the only correlation that we know right now is that if from the same region, same source, one CME has already erupted, the second CME, when it erupts, it becomes easier. Why? Because it has disrupted the strapping field lines. Okay, so you have a flux loop like this, and it is embedded in the sun, and you have coronal loops, which is covering over the flux loop. So if a successful eruption happens, this flux loop will tear apart this overlying loops. Okay. So now, if this active region again becomes energetic in a very short interval of time, then the second flux loop, when it erupts, it becomes relatively easier for the flux loop. So usually what is seen is that the second CME is faster than the first CME. Yeah. No, easier for the CME to erupt, to go up. Okay. So, I mean, let's say you are standing in a queue, in a big crowd, and waiting for the bus. So if some part of the crowd has already got into a bus, it will be more easier for you to get into the next bus. It's the same thing for the flux loop. You have your strapping field lines on top of it. So if the field lines are disturbed by some earlier lying flux loop, then it becomes easier for the flux loop lying in the bottom as a second flux loop to erupt. No one is stopping that. The hindrance is lesser in that sense. Hungry? Sure.
So all of you remember to wear the badges when you're going for access, or when you're around during the conference. This also helps you identify among your works, right? You can interact with other people as well. Please remember to wear the badge.